Chapter 1, Energy. Work done by a constant force. Work is done on an object when a force causes a displacement of the object. In physics, the work is given by WF equal F scalar D, where F is the forces and D is the displacement of this force of this object. So F scalar D equal to F times D times cosine FD, where FD is the angle between F and the displacement D. So alpha is the angle between F and D. If alpha between 0 and pi over 2, the work is positive, then the forces is a motive force. And if alpha between pi over 2 and pi, then the work is negative, then the forces is a resistive force. And if alpha equal pi over 2, no work. For example, if alpha equal pi over 2, like the reaction of support. So the reaction of support is always perpendicular to the displacement. Then the angle between the forces and the displacement equal to 90 degrees, equal pi over 2. So no work. So the work of reaction of support equal to 0. A force perpendicular to the displacement of its point of application does no work. The unit of the work is joule. Now, work done by the weight along any path. Work of mg equal the force mg scalar the path AB. We have AB vector equal xb minus xa I plus yb minus ya j. And the weight is along y-axis in opposite direction. So mg vector equal minus mgj. So we obtain minus mgj scalar xb minus xai plus yb minus yaj. We have j scalar I equal to 0 in math. Since j scalar I, j and I, they are perpendicular vector. When two vectors are perpendicular, the scalar equal to 0. And we have j scalar j equal to 1, since they are collinear. So finally we obtain work of mg equal minus mg yb minus ya, when yb equal to h b and ya equal to ha. The path is starting from A, so HA is the H initial. This is H initial, and it's end at point B, so HB is the H final. So we obtain work of mg equal mg times h initial minus h final. Now work done by a constant moment, all about rotation is cancelled for LS section, so this part is not required. Now power. Average power, P average equal delta W over delta T. It means delta work over delta T. Instantaneous power and translation. If F is constant, P equal F scalar V. It's so important. Instantaneous power and rotation is cancelled since is not required for LS section. The unit of power is in watt. Now, mechanical energy. First, kinetic energy. The kinetic energy is the energy that related to the mass and the velocity of an object. So a body of mass m moves at a speed v has a kinetic energy such that Ke equal half mv square. Ke is in joule. All energy, the unit of energy is in joule. Rotational motion is not required. At maximum height, at maximum elongation, at maximum compression, at maximum altitude, in all this case, the velocity equal to 0, then the kinetic energy equal to 0. Work energy theorem. The work energy theorem is delta Ke equals sum of work of all the forces. Example, delta Ke, it means Ke final minus Ke initial. So half mv final square minus half mvi square initial square equal work of weight, work of normal reaction, work of friction, not the work of friction. It's equal always F times D times cosine 180. So WF equal minus F times D. Then the work of friction is always minus F times D. Efficiency, it's equal to P useful over P total consumed, output over input in energy cases or in power cases. Gravitational potential energy is the energy that depends to the position. So it is a positional energy. A body of mass m and has a height h with respect to a reference. We need a reference to calculate gravitational potential energy. So this is a reference. The object maybe is on the reference, maybe is above the reference, and maybe is below the reference. If a point is on the reference, then the GPE is equal to 0. Why? Since on the reference, no height. The object has no height. But if the object is above the reference, GPE is positive, then the GPE equal plus mgh. And if the body is below the reference, GPE is negative, then GPE equal minus mgh. We have delta GPE equal minus work of mg of weight. Elastic potential energy. Hooke's law T equal K times X, and the restoring force equal T equal minus KX I. It's opposite to the displacement of the spring. And the elastic potential energy EPE equal half KX squared. Each spring has an anti-length or free length L0. When an object is attached to the spring, the length of the spring become L. In this case, the spring is elongated by X. X is the elongation. Where X equal L minus L0. So X in the EPE equal to L minus L0 is the elongation. Okay, in the compression case, this is a spring. This is an object that compresses the spring. In the first spring, the length of the spring is L0, while in the other is L. This part is the compression is named by X. So X is the compression. In this case, X equal L0 minus L. Now, conservative system. Conservative system, if friction equal to 0 and if the conservative forces are acting, in this case mechanical energy is conserved. Then delta ME equal to 0, therefore mechanical energy before equal mechanical energy after. If friction different than 0, then friction is exist, so mechanical energy is not conserved. Therefore, delta ME different than 0, then delta ME equals sum of work of non-conservative force. The non-conservative forces is the friction, and we have another forces without weight. The weight is a conservative forces. So the work of friction equal to minus Fd. So in the case of friction is exist, delta ME equals sum of work of non-conservative forces equal work of friction plus the work of non-conservative force equal minus Fd plus etc. Internal energy, microscopic. It's mean inside an object. So the internal energy is the total energy contained within a system due to the motion and interaction of its particle, including atoms and molecules. So the internal energy is the total energy. So the internal energy is the total energy from all the atoms and molecules contained within your system. It includes two main types of microscopic energy. We have microscopic kinetic energy and microscopic potential energy that depends on the molecules and the atom. Okay? Total energy and its conservation. that total energy E of a system is the sum of its internal energy U and its mechanical energy ME. So the total energy E equal U plus ME. So we have E is the total energy, U internal energy, and ME the mechanical energy. A system is energy isolated if does not exchange any energy with its surrounding. In this case, its total energy is conserved. Okay, an isolated system is a type of a thermodynamic system that does not exchange matter or energy with its surrounding. In other words, neither heat nor particles can enter or leave an isolated system. So, when the system is isolated, the total energy E is conserved. So delta E equal to 0. So we have E equal U plus ME. We obtain delta E equal delta U plus delta mechanical energy. When the system is isolated, so delta E equal to 0 since E is conserved, then we obtain delta ME equal minus delta U. As a summary of this chapter, we have mechanical energy equal ME equal KE plus GPE plus EPE. Kinetic energy KE equal half mv square. Gravitational potential energy GPE equal plus or minus mgh equal plus mgh if the object is above the reference, minus mgh if the object is below the reference, 0 if the object is on the reference. Elastic potential energy EPE equal half kx square. Elongation or compression of spring x equal delta L equal L minus L0 in absolute value. Restoring forces T vector equal minus kxi. Hooke's law T equal ka times x. If friction and the non-conservative forces are negligible, then the mechanical energy is conserved. So we obtain ME before equal ME after. If friction and the non-conservative forces exist, then the mechanical energy is not conserved. So delta ME equal work of friction plus work of non-conservative force. So we obtain ME after minus ME before equal minus F times D, since the work of friction equal to minus F times D plus the work of non-conservative force. If we have work energy theorem, delta kinetic energy equal work of friction plus work of reaction of support plus work of weight plus etc. Work of F of any forces equal F scalar D equal F times D times cosine FD, the angle between F and D. Work of mg equal mg times h initial minus h final. Work of reaction of support equal to 0. Reaction of support perpendicular to the displacement, so the work of reaction of support equal to 0. Work of friction equal F times D times cosine 180 degree equal minus F times D. Delta GPE equal minus work of mg. Okay. Newton, as a revision, Newton's second law. First case, in this case, the object is on the horizontal surface. So we have two forces, weight and reaction of support. By Newton's second law, sum of forces external equal ma. All the forces they are reaction of support plus weight equal ma. Projection along the motion, reaction of support and weight, they are perpendicular to the motion. They are on the y-axis. This is the y-axis. And this x-axis, the motion is along x-axis. So 0 equal ma, we obtain a equals 0 meter per second square. So the motion is uniform rectilinear motion. Therefore, velocity is constant. In the second case, the object is on the horizontal surface, but the forces acting on the object, they are friction and weight and reaction of support. So by Newton's second law, sum of force external equal ma. The force external, they are work, friction and reaction of support equal ma. Projection along the motion, the work, the weight and reaction of support are cancelled since they are perpendicular to the motion. This is the motion x-axis. So and the friction force is opposite to the motion, so we obtain minus friction equal ma, then minus F equal ma. In the third case, we have inclined plane like this. The motion of the object is downward, so we draw the x-axis downward, and this is the y-axis. The forces acting on the object, they are weight and reaction of support, and this is the angle alpha. We must project the weight on the y-axis and the x-axis. So this is wy, and this is projection along x-axis, and this is wx, and finally this is the angle alpha. It's opposite to wx. So applying sine alpha equal opposite to hypotenuse. So the opposite sides of alpha is wx, and the hypotenuse of alpha is w. So we obtain wx equal w sine alpha, then equal mg sine alpha. So applying Newton's second law, sum of force external equal ma. We have reaction of support plus weight equal ma. Projection along the motion, wx is on the side of x-axis, so it's plus wx equal ma. So we obtain mg sine alpha equal ma. The fourth case, case 4, the object is upward. Alpha, this is the object, and this x-axis, this y-axis. The forces are reaction of support and weight. We must project w on the y-axis, wy, and on the x-axis is wx. This alpha, we apply sine alpha equal opposite to hypotenuse. We apply sine alpha equal, we apply sine alpha equal opposite to hypotenuse, so sine alpha equal wx over w, then wx equal mg sine alpha. So apply Newton's second law, sum of force external equal ma. We obtain R plus W equal ma. In this case, Wx is on the opposite side of x-axis, so by projection minus Wx equal ma and the reaction of support equal to 0. So we obtain minus mg sine alpha equal ma. Note, it's very important, the derivative of v square equal to v prime, and the derivative of vp is equal to a, so v prime equal a, then the derivative of v square equal to va. The derivative of x square is 2x x prime, and the derivative of x is v, so the derivative of x square is 2xv. The derivative of v prime, it's a, and the derivative of x prime is v. And dv over dt is the symbol of the derivative of v, and dx over dt is the symbol of the derivative of x. Okay. As a revision, uniform rectilinear motion, the time equation is x equal vt plus x0. In uniform varied rectilinear motion, we have two time equation, x equal half at square plus v0 t plus x0, v equal at plus v0, and we have v square final minus v square initial equal to ix. At maximum height or at maximum compression, velocity equal to 0, kinetic equal to 0. Power P equal delta work over delta T, or delta mechanical energy over delta T, or P equal F times V. The forces, they are weight, normal reaction of support, friction, braking force, tension of spring, tension of string, traction force. Internal energy U equal kinetic energy microscopic plus potential energy microscopic. Total energy E equal U plus mechanical energy. It's mean internal energy plus mechanical energy. If the system is isolated, the total energy E is conserved. Then delta E equal delta U plus delta ME. So we obtain 0 equal delta U plus delta ME. Then delta U equal minus delta ME. Kinetic energy equal ME minus potential energy. Potential energy equal mechanical energy minus kinetic energy. If the kinetic energy equal to the gravitational potential energy, we have KE equal mechanical energy over 2, and the GPE equal mechanical energy over 2. If KE equal GPE, and there are no EPE. So we have ME equal KE plus GPE, and if KE equal GPE, so we obtain GPE plus GPE. We replaced KE by GPE since they are equal. So ME equal to GPE. Therefore, GPE equal ME over 2. And since KE equal GPE, so KE equal ME over 2. If friction equal to 0, the mechanical energy is conserved. So the representation of mechanical energy is a straight line constant, horizontal constant. Finally, the pendulum. This is a free pendulum, and they are theta. From this particle to this level, name H. So this is H. The length of the pendulum is L. So this L, they are equal. We name this side by Y. So H equal L minus Y. In another case, Y is adjacent to theta. So by cosine theta equal adjacent to hypotenuse, cosine theta will obtain y over L. So y equal L cosine theta. So h equal L minus L cosine theta. Then we obtain h equal L parenthesis 1 minus cosine theta.